So, during previous lectures, we have considered the classification of structural types, structural schemes, and structural systems, and the overall classification of building we can consider in this table. So, the highest level of classification called structural type, and there are three main structural types: mullion beam, multi-touch, and suspended system. And also we have considered structural systems: frame, load bearing, mixed, and all these classification is included in mullion beam in this only one structural type. And uh, each of these structural systems has a next level of sub classification called structural schemes. And a structural scheme is a variant of structural system which describes the orientation in space of load bearing elements of this system. So next lecture was devoted to the special stiffness and stability of buildings, and we have considered main differences between stability of form and stability of position. And we remember that the most important mm, goal of structural type is to protect the building from a loss of stability and loss of stability of position, and we have to design buildings in that way, so we exclude the loss of stability of position, so it has to be stable, though our building has to be stable. And also we have to take into account the stability of form. It is a local type of stability, and if stability of position it describes the overall behavior of building, then the stability of form describes the stability of separate load bearing elements. And a special stiffness, next important term that we will use in further, it is the ability of separate elements and the entire building not to deform under the action applied forces, to be able to maintain geometric stability. And we know that we can guarantee the geometric stability in two main ways. So first of them is the link method. It's we can make it by adding link elements, and the second way is to make rigid connections between elements, and it is a frame method. Nevertheless, if we will consider the behavior of triangle, we will see that it works like a geometrically stable system, because this system, which consists of the rod elements with in connection between them, we can see that it is also a rigid system which is geometrically stable. And when we were considering this situation, we remember that the minimum amount of link elements or rigid elements which we can include in the special scheme of the building is enough for that enough for our building is only one. So only one link element can redistribute internal forces in that way to save the stability of the overall structure. So one link in this way, one link in this, also a link in this direction, in this and this, and you can see the roof elements. They also the slab elements. They also consist of such link elements. And when we discussed the ways how to implement those terms in real life, and we remember that when we talk about steel frames, we can use a frame method of creation of geometrically stable system. We can also use a link method by adding such elements, or we can use frame link when in one direction we made a link method to create a geometrically stable system, and the another when in the another way we are making rigid connections between elements. When we are considering, for example, reinforced concrete frame, in this case we also can use rigid connections between elements, and we can use links. But when we're talking about reinforced concrete buildings, the rod elements are not enough to make geometrically stable such a heavyweight structure. So that is why the role of links in such structural schemes, in such structural systems, can play reinforced concrete walls. Uh, Rigid walls can give the necessary geometric stability for a building. And when we are talking about masonry buildings, the only one option that we have to create the geometric stability of system is a link method. So only link method can provide us a geometrically stable system in masonry structure. So, and this table helps us to understand which type of geometrically stable of creation of geometric stability we can use to make it in the most efficient way. So when I'm talking about load-bearing walls with masonry walls, for the building with masonry walls, the only option that we have is a link method. When we're talking about reinforced concrete frame, the preferable method of creation of geometrically stable system is a frame method. It is rigid connection between beams and columns, or beams or columns and slabs, something like that. And a link and frame link are also possible, but for reinforced concrete structures, frame method is preferable. And when we're talking about steel frame, the preferable and the cheapest is the link method, and frame and frame link method are also possible for such structural schemes. But then we have considered deformation expansion joints, and when we talked about them, and we agreed that if we will not design expansion joint in the building, when in that case the joint will arise anyway, and we will find it anyway. But if we will design it in that case, our deformation expansion joint will look exactly as we want. But if we will not consider the presence of expansion joint in the building, in that case we will find a significant problem, because in that case that expansion joint will arise at our walls, at our slabs, and it will look like a big crack. In some cases, it's huge cracks in the walls, in the slabs, and something like that. And first type of expansion joints that we have considered, it is a thermal joint. It is thermal expansion joints, and we are making such kind of joints because of the thermal expansion of the building during the warm period, or vice versa. It's a subtraction of the building, contraction of the building during the low level temperatures. So that is why we can split the building on the thermal expansion joints by creation double columns, which are based on one foundation. So, and very important about the thermal expansion joints, that we have to know that thermal joints are not splitting the foundation. Why? It is connected with this with that our constructions which are located underground are almost always in the same temperature, because underground, on the deeper than 1 meter from the surface, we will find exactly the same temperature. It's like something like 12 degrees of Celsius. So first expansion joint split the building on parts, but the above ground part of the building, but it not splits the underground part of the building. Significantly differs from that kind of expansion joints. We know settlement joints. Settlement joints are used in building for for the cases when we have situation with uneven deformations, it may be caused by soil condition, it may be caused by the situation when we have at the same ground the building with the amount of floors. For example, in the same complex, we can have a building with 8 floors and, for example, 20 floors. One of my residential complex that I've designed has such situation. So, and for these cases, when we have a situation with uneven deformation, which is caused by uneven loads on the ground, we can find the solution of this problem by splitting the building on parts, and those various parts have to be separated one from each other, including foundation. And the main difference between settlement joint and temperature joint is lies in that our foundation has to be also divided by joint. Next kind of joint is a shrinkage joint. It have to be done into the reinforced concrete or concrete floors. And if we will not make those expansion joints, we will find cracks in our floor or reinforced concrete elements. And to protect it, we are using also shrinkage joints. And last type of joints of between the buildings, it is called anti-seismic joints. Anti-seismic joints are used to protect building of pounding effect when during the earthquake. May be this situation when each building shakes with its own form of vibration, but sometimes we can find a situation where buildings are not shaking like this, but they have a pounding effect. And to protect several buildings from this pounding effect, or the effect of when one building kicks the another one during the earthquake, we have to find a situation when one building is situated on such distance when during the earthquake it is impossible to make stroke effect, the kick effect, the pounding effect on its neighbor part or the neighbor building. So, and here is the main difference between anti-seismic joints and other kind of joints, because thermal joints, it is for the horizontal and also vertical deformation during the vibration of the temperature during the changes of the temperature. Settlement joints, it is to protect the building from these uneven deformations. And when we're talking about seismic, anti-seismic joints, it is for the protection building of this kind of effect of pounding between various parts of the building or between various buildings. Here are the types of joints into the floor. So we can use these buildings with such joints, and sometimes when we are moving through the big trade center, we can even define where is the joint located. But sometimes our stroll which we are moving with which we are moving during across the trade center, we can find that our stroll jumps, and those jumps are connected with the expansion joints which are located in the floor. So here the two main topics that we have already considered, and I've just reminded to you. Do you have any question about them, or everything clear? Alexandra, any question?
Поки що ні.
Okay, so let's move further, and I will explain you next topic, and it is the third lecture. It's called the features of the work of flexible elements in continuous and frame structure. So right now I will explain you a few main principle of work of various bending elements, which is very important for you as a future architect. And these topics are really important for you from the next point of view, because when we will consider the difficult ground conditions, when we will consider such situation like landslides, rock falls, or subsiding soils or something like that, we have to take into account that the behavior of building which is located above such kind of difficult ground condition significantly depends on the type of structural system and type of behavior its load bearing element. So that is why during this lecture we will consider the difference between the behavior of continuous beam structures and the distribution of internal forces compared to the simple supported beam. So, for example, we have such situation. Here is the single span beam and multi-span beam. For the from the first sight, it's something like they really look like each other, but the difference between them lies in the amount of support elements. And for this case, we have three support elements, and for this case, we have only two. And it is very important for us to understand that sometimes the amount of supporting elements are not playing significant role on the behavior of elements. And why is that so? Because sometimes beam with three spans can work with like something like this. In this case, we can see that each span works as a separate element, and in this case, we can see that it works like one continuous beam, and the difference between them lies in the redistribution of internal forces. And I will show you how this redistribution impacts on its behavior. For example, on the from the left, you can find the simple supported multi-span beam, a simple supported beam, and here you can see that we have span bending moments, and we don't have any support bending moments. But for this case, we can see that we have a support moment. So the main difference between a single supported beams and continuous beam, we can see that the difference lies in that we have almost the same bending moments, but this value in this case is concentrated only in the span, but for this case, for continuous beam, it is redistributed between support and span. So these additional support and this behavior of building like a continuous beam gives us an ability to redistribute bending moments from the span and to relocate it to the support of the building. And same situation when we are talking about multi-span beam, which is loaded by concentrated single span load. For example, if we will give the load for continuous beam, in that case, we will see that this bending moment is redistributing in this and also in this span. When we locate the load into the central span, we can see that this bending moment is also redistributed into the neighbor to the spare to the neighbor elements. And when we will compare this behavior with the beam with cantilevers, we can find same situation. Cantilevers gives us an ability to redistribute bending moments. And for example, here is the simple supported single span beam without cantilevers. But when we are adding a cantilever with the span half of the work span, in this case, we will get this moments at the support and zero and this kind of moment in the central part of the beam in the central span. And when we are taking cantilevers with the span one third of the working span of the building, so it is 33% of this span. In this case, we will get the equal moments in the at the support and in the span. And it is a very important question when we are talking about when we are considering situation with the cantilever elements, because all architecturally interesting buildings with beautiful architects, it's almost like 100% situations which is connected with huge cantilevers. Only cantilevers are not the only elements which gives the architectural expressiveness for the building, but nevertheless, it gives us ability to make something that looks like unique. And this you can see in these elements or even bridge elements with which works according to the cantilever like a cantilever. By the way, this is very interesting and already built building. It also consists of huge cantilever elements, and here how it was built. You can see those truss elements, which serves to this building like load bearing elements, and those trusses are supported by the columns which you can see over here. Such situation you can find in a solution like which like this. It is also gives an ability to redistribute this moment and make a huge cantilever by adding such elements and such trusses to redistribute internal forces. Some more solutions. Next question. So before I have started the next question, do you have any question about continuous and simple supported bending elements? Any question? So if you don't have any,
No,
oh, that's great. So let's continue. Next question, which we will consider during our lecture, it is the behavior of slabs. And if you will look at these two pictures, you will find that like those buildings very look like each other. Both of them has columns, but if you will consider this situation in details, you will find that in this case you have four columns, in this case you have six columns, in this case you have two beams, and in this case you have five beams. And difference between behavior of this and this slab lies in that this slab works only in this direction, but in this case, when we are considering such structural system, you will find that these slabs works in this direction and in this direction. It is, and it depends on the ratio between these spans. So, if in we're considering the behavior of such situation when the ratio between these and these spans are less than two, in this case, these labs works like a bimomental slab. But in case when we have a situation where our span is more than two times bigger than the another one. So when the ratio between those spans is more than two, in that case we will consider this slab like a one direction slab, and so the design reinforcement will be located in this slab only in one direction. So next question which we will consider during this lecture uh, is connected with the types of reinforcement of such slabs. Before this lecture, when we were on our first lecture, when we tried to consider the structural schemes of frame structural system, we found that we have various variants of frame structural system. We can define that we have with slab frame building with longitudinal beams, with transverse beams, with orthogonal beams, and with flat slabs. And flat slabs buildings is most widely spread in residential construction. And it is that is clear. Why is that so? It is connected with the situation with the beams, because in this case it's very easy for us to create such to make such a slab at the construction site, and it saves the space of our under our ceilings, because flat slab don't need any additional uh, cardboard ceiling or stretch ceiling, so we don't have to make such structural solution, because flat slab is really comfortable for construction. And we have two types of such slabs. It can be defined as the flat slab with hidden beams, because physically we can see those beams in such slabs, because the slab is flat, but reinforcement of this slab is performed in that way that then it is hidden from our eyes, but internally the reinforcement is located in that way that it behaves like frame structural scheme with crosswise arranged beams. In some cases, we can use another type of reinforcement. It is reinforcement with flat grids, and these makes some solutions much difficult, and I will explain you why. Because when we are trying to reinforce our slab in this way, when we are using flat meshes or grids to for reinforcement of uh, such kind of slabs. Sometimes those meshes are created are made at the construction site, and you can see those separate roads which constructors locate orthogonally one to each other and bending it with the wires. But sometimes these meshes can be created uh, at the plant where we have mesh welding machine. So the difference between the hidden beams and the reinforced slabs reinforced with meshes lies in that in this corner, because in this node, in this connection element, because we have a huge concentration of internal forces on the columns, and to protect the building from shear failure, we have to use transverse reinforcement. And location of big amount of transverse reinforcement in these elements reduces the ability to locate various openings inside slabs. For example, architects really like the situation when we have sewerage pipelines or ventilation openings near the columns, because it is a vertical connections, and it is logically when we have a vertical load bearing element and near located ventilation or sewerage pipelines. But when we are using this kind of reinforcement, it is really hard for us to locate the opening. So for you as a future architect, it's really important to understand that it is not good solution to locate openings around the column, because it cuts our slab from load bearing columns. Typical solutions of how can we protect our slab when we are making openings in it. So next. important moment that we have to take into consideration when we are designing flat slab buildings. We have to know that spans with the spans more than 7.2 meters. And when we're talking about seismic regions with the span of more than 6.6 meters, it is necessary to use beams or other beam or grid structures. So, for example, it may be caissons. But for example, when we're talking about our Odessa airport, in that case, we use it to design it flat slabs with the span 9 meters. But for your understanding, regular flat slabs has a thickness of 0.22 meters, so 22 centimeters. But for that case, when we have to design a span with span 9 meters, we use a slab with a thickness 0.4 meters, so 400 millimeters. But it is really expensive, but it was necessary for that case, because the span of the roof at that building is not 9 on 9 meters, it is 18 on 18 meters, so that gives additional space. Next question. Sometimes for big spans we can use caisson slabs. And for example, we can use caisson slab for the spans with the value 34 on 34 meters. The height of such structure is 1/20. So for this case, it was 1.7 meters the height of this slab. So it's like something like that. I have a height is 1.94, and here is the height from the level of floor of that slab. But sometimes, by the way, caisson slab, it can also be called waffle slabs. And sometimes for because sometimes when architect don't like such solution, he can use hidden caisson. It's this type of slab called nautilus. It is made of plastic elements, which reduces the own weight of the slab, because in the middle of the slab the internal forces are not so big compared to the lowest and the upper zone. So that is why this part of slab can be filled with such plastic elements, and that reduces the own weight of such construction and concentrate all internal forces where are they expected, on the upper and on the lower part of the building. So when we're talking about frame build, by the way, do you have any question about slabs or beams or other kind of bending elements that we have already considered? Alexandra, any question?
Все зрозуміло.
Okay, so next question that we have to consider during our lecture is connected with frame structures. So frame structures are also very widely used constructions in architects practice, and that is why it's very important to understand what kind of frame structure do you have in your case when you are designing the reconstruction or even designing a new building. What type of frame are you using, and what type of frame have you used to design the building correctly? There are various kinds. From the first sight, it looks like it's exactly the same. But if you will compare this in details, you will find out that it is a regular single supported beam with columns which are stiffly connected with the ground. In this case, we have a beam, continuous beam with cantilevers, and here we have a rigid connection, rigid frame in the upper nodes, and uh, Soft connection. What? One moment. It's not a soft connection. I forgot this word. Charnier. Charnier. Moment. Hinge connection, yeah. And in this case we have a hinge connection between column and a foundation. So, and this kind of connection between beam and column, column and foundation, column and beam with cantilevers gives us various variants of distribution of internal forces. In this case we are talking about bending moments. Those are additional types under the vertical loads, and you can see that the internal forces, the values of internal forces depends on the type of the frame which we are using in our case. Next important difference that we have to consider, we have to take into consideration, it is the behavior of the frame structure under the lateral loads, something like wind or seismic impact. This is very important also to understand when we are designing our building to withstand the horizontal impacts, for example, seismic or wind effects. We have to understand which type of connection between beams and columns we have to design. And in this case, you can see that we have rigid connection of columns with foundation and hinge connection between column and beam. For the difference between this and this one lies in that we have hinges in the lower part and a rigid connection in the upper part of the building. So, and when we are talking about horizontal impacts, in this case, all horizontal impacts are concentrated on columns, and in this case, the horizontal impacts are redistributed between vertical and horizontal elements. So that was all that I wanted to talk with you today about third lecture. Next topic that we have to discuss today, it is the lecture number 4, and it is connected with the high-rise buildings. Do you have any question about previous lecture, about third lecture, beams and frames? Or everything clear? Is clear? Is everything clear? Alexandra, hello? Alexandra? So I hope you understood everything very good and clear. Everything clear. So next topic that we will discuss today during this lecture, we have to discuss the high-rise buildings. So first question that we have to discuss, it is the classification of multi-story buildings, and we have standard classification from 1966, 76, which tells us that there is three level of multi-story buildings, and up to 50, up to 75, and up to 100 meters. And with the height of more than 100 meters, it is a high-rise building. But when we are talking about classification of multi-story buildings, it is also has various ranges of floor amounts. For example, low-rise building, it's less than 4 stories. When we're talking mid-rise building, it's from 4 till 12, high-rise 12 till 40, and skyscraper is less than 300, but more than 40. Super tall is more than 300 meters, and mega tall buildings is more than 600 meters. It's various international classifications, various approach to this. But when we are talking about our Ukrainian classification, we have a situation where we have that three limits. So first limit is 73.5 meters. If your building which you are designing is higher than 73.5 meters, it's a conditional height. You remember what is conditional height? It's not the overall height of the building. It's not the height of the highest point of the building. 73.5, it is the height of the highest floor where can be people located. And this limit is connected with the fire alarm ladders, fire systems and fire ladders. So next limit that we have in our codes is 100 meters. 100 meters from 73 till 100 meters. It's a limit for the residential building, and for the public office building it is 150 meters. So not more than those values of amount of meters in height of for the building. So here is our local Ukrainian classification. More than 73.5 meters, it's high-rise buildings, and the highest limit for the residential 100, and for the office building and public building 150 meters. When we are talking about such high building, we have to consider that the foundations for these buildings have to be also very massive. And the regular practice for such buildings is to use board pile or prefabricated piles pile foundation for these buildings. Maybe it can be made of barrettes. Barrettes, it's such kind of foundation. It's like walls in the ground. So a huge machine excavates the ground, and we locate reinforcement there, and then we are pouring the foundation, making the concrete inside of it. So that gives us an ability to create a foundation called barrettes. Next is a slab foundation. It can be used for the multi-story building, but it can be used in the variant of box shape or flat slab. Sometimes the thickness of such slabs may be 3 or even more meters, but this type of foundation can be used only in case when we have a good ground conditions. But never you have to remember that never we are not using separate foundations for multi-story building. Sometimes we can use combined with slab with piles, but it just a slab or a slab with piles. It depends on the value of the quality of the ground. So next question that we have to discuss is the structural systems of multi-story buildings. Structural systems of multi-story buildings is really it's like the same compared to the regular building, but not the same, because in this case we have a frame structural system, and that's okay. That's normal for us. We can find the variant with so frame building. We have find the shell building. There is no such type in regular building. We can find the wall or diaphragm system and the core system. Shell, where is it's not slab, sorry, it's mistake. C is a wall diaphragm system, and D is a core system. So see here you can see the crosswise arranged walls. You know this and this system from the regular building, but this type is the core system, and we will discuss furthermore in details. So, for example, we will consider few buildings and various structural systems with almost similar amount of floors. For example, frame building with rectangular columns with the span 5.7 meters, and in this case we have one significant problem for this building, and I will show you what is that problem. So next variant for such kind of building, it called uh, core in tube or double tube, and it this kind it is core in tube because tube and perimeter consist of columns with beams, and in the center we have a core. In this it's called double tube. It is two tubes which consist of vertical and horizontal elements, and variant of multi-story buildings. It is also shell building, and it is the fachwerk shell facade and facade shell. It is also look like the same. But as we talked previously, high-rise building can be also with wall diaphragm system, and here is the system which use Odessa construction company Budova for their building, and it is also really steep for multi-story building and with a good reserve of construction stability. Also, there is a core structural system for the high-rise building, and there are two types of core buildings with suspended floors and with floors which is located on the compressed columns. So suspended hangers. Yeah, you can see there is no columns over there because these floors are hinged to this core, and this variant with the compressed columns. And this type of building is really good and really interesting. From the architect's point of view, it gives an ability to make something interesting with something expressive. Variants of creation of such structural core of the building, and sometimes core buildings can have more than one cores, and here is the famous situation where multi-story building with two cores was designed that way that the concentration of the wind in the lowest part of the building is such huge and such significant that it blows out the people who are walking over in the tube during this strong winds. And on examples, as I told you before, we will compare few of these structural schemes. And for example, when we're talking about multi-story frame building, in this case, we have not big span, 5.7 meters, but you have to know and you have to admit that this cross section of this column is over big. It is the cross section of this column is meter on 1 meter. So the distance between these columns is not 5.7. 5.7 is the distance between axes, but between the surfaces of the wall of the columns you will get on 1 meter less, so 4.7 meters. So much floor surface is under the columns. And here is the cross section of this column meter 1 meter on 1 meter. And here you can see the cross section of the frame building, and here is the core in tube building. It is also has 40 floors, but in this case we have a deal with big spans. It is 48 meters, so the distance between these and this wall is 16 meters, and it is been built in this way. Here you can see columns, and between those columns we have beams, and in this direction we have slabs which are located in this way, and in this way. So this gives a huge space, 16 meters. For example, if you will compare it with the previous one system, we have only 4.7 meters between the columns, and in this case we have almost 16 meters between the vertical load bearing elements, and it gives us an ability to make a huge office premises or trade premises, and that's good for such kind of building. And in this case, we have a cross section of columns of the exterior tube. 850 millimeters on 850 millimeters, so 85 centimeters on 85 centimeters. And in this case, for the middle, for the center count, we have meter on 1 meter. But we have huge spans for such kind of a building. And another type, it is a core double tube building. The difference between this and previous one lies in that we can see here the walls with the big thickness. The thickness of such walls equal 800 millimeters, as I remember. Yeah, 800 millimeters. So it is very huge building in the center. This building is much stiffer compared than the previous one, but it is really huge for seismic regions with not such a big amount of floor. That is clear, because 40 floors building in seismic regions will look not the same like this one, but it is rigid enough to withstand the significant wind impact. So that's all that I wanted to discuss with you during the first model. So we have considered structural types, structural schemes, structural systems. We have considered what is geometric stability, and then we have considered the behavior of slab and of beams, of bending elements and frame elements. And this lecture that we have considered right now was devoted to the high-rise and multi-story buildings, and we have analyzed the behavior of building with such a big amount of floors and from the architectural point of view. So how can we make this same amount of floor with various structural solutions? So that's all for today. And according to this material, next week I propose you to make a model. What do you think, Alexander? What do you think about the model on the next week? On all, based on all this material. Alexandra, can you hear me? All right.
Да, я слышу.
Yeah. So next week I propose you to make a model. What do you think about it, based on all this material?
Повторіть, будь ласка.
Наступного тижня я пропоную вам зробити модуль по цьому матеріалу, що ми з вами сьогодні згадали, і той, що переглянули тільки що.
Добре, а що за модуль?
Тобто, коли почнеться на 8:30 наступної п'ятниці, приєднуйтесь і зробите там, скільки буде 20 питань, наскільки я пам'ятаю, обрати найбільш правильний із запропонованих мною варіантів і все.
Добре, це оцінка, яка буде впливати на ітогу, так?
Yeah, it will make an influence on your final score.
Окей.
Okay, so thank you, goodbye, see you next week. Bye.
Thank you and you, goodbye.